Okay, so we're going to be spending the next several lessons or lectures talking about I2C communication and how to quote write APIs for us. So let's kind of just go through here. I'm going to be switching between programs here. Let's go to the PSOC program here, and let's go ahead and create a new project. We're not going to do anything um, exciting for this here. Come on, new project. There we go. I'm not going to give it any kind of fancy name or anything of that nature. And then I'm going to just do a pin here, and I'll just do let's just do a digital output pin here. I'm not even going to carry pin 1. I'll just leave it as strong. I'm not really doing anything with this. I'm just trying to show you here. So, we know that, okay, well, we call it something in particular. Maybe we connect it up to a PWM signal. But then before we actually start writing our code, like our main.c, we generate the application. And goes through here in a second. And I know I didn't assign it to a particular pin. I don't care what pin it gets assigned to. What I'm more interested in is, of course, right over here we have our source file. And then as this gets generated here, we get all these generated source here, all these APIs here that are built here automatically for us. So what I'm trying to illustrate with this, and we can open some of these here, is, and I think we've even looked at this before, if you look in here, there's pin1 and .c and pin1.h. If I double click on the pin1.h and open that file, that's what's called the header file. There's some other things in here, but first off, it has some other header files that's including there, which are, you can think of as kind of libraries. And come on, there we go. And then they have data structures being defined, and here we also have function prototypes. The unsigned end pin1 read void, so that's telling it it's returning an 8-bit unsigned integer and it has a void input on it. Here's the right one where, okay, it's a void, there's no output from the function, and the value. And so there's a lot of things in here, and then there's a bunch of pound defines here, some macros that are being defined for us, a lot of which we don't use, a bunch of other things as well. But we can see the important thing here is we can say, hey, some of these, and then there's also the clear interrupt, the set interrupt mode. These are all things that we've had to use before based off of the type of pin. Now, whether it's an input pin or an output pin or an analog pin, the functions that get generated are going to be different because the program knows, okay, well, in this configuration I have to define these particular functions. And then if I go to the C file, we can say, okay, it says include the pin1.h, and I'm going to select, but then you can go down through here, and there's the set drive mode, but here we can see pin1 write, and then this is actually the code that gets executed. So when you call the pin1 write function, if you're, like, for instance, turning the red LED on or off, this is the code that actually gets executed here. Now, we don't really worry about that. That's kind of all done behind the scene. And there's all these other different kinds of bit shifting and masking going on. And as far as if you want to see what those are and you want to look into that in more detail, if you look up in the aliases, you're going to see some of this, shifting here and other things of that nature as well, defined in the aliases as well as in the header file. Now the reason I'm talking about that is if we go back to the top design, remember if you double click on this and there's that data sheet that we get to have here, we go to the application program interface, and then we have where these general API functions, that we already kind of saw where there was those function prototypes here, and we have all of these sitting right here. Now, The difficulty becomes when we try and hook up external sensors to this device, because these are all just kind of built in on the board, or some basic things like, okay, the GPIO pins, it's fine to just have these here, but what happens when, okay, I'll have a pin as a GPIO or something, but I'm wanting to actually, hook up a sensor or communicate with a device, or maybe just do an analog read, which we've done with the potentiometers. But what happens when I want to hook up, for instance, the device we're going to look at here, and you'll all have one of these, is a miniature I2C digital barometer. So it's really designed to measure pressure. It can also be used to measure temperature. So it says it's optimized it for barometric measurement applications, but you can actually use it to measure temperature. The temperature isn't as accurate on this one, but the pressure is actually pretty accurate as far as the pressure measurements. And then it gives you application examples, hard disk drives, even altimeters, barometer, portable desktop, all sorts of air control systems, all sorts of things that you can use this for. And then it gives us a block diagram, but the key thing here is that there's these SCL and SDA lines, and that these are the I2C ones, and there's these 4.7 k ohm pull-up resistors that you need in order to make sure that you pull those up to high voltage, because remember with I2C you only pull things down to the low. And then this is of course your little microcontroller, and then you can also connect the reset and shutdown. We actually aren't going to use those particular buttons there. But we're going to go through this data sheet here in a little more detail in a second. But if I go back to my PSOC program and I try to say, okay, well, I want to try and find that here. Well, if I do an MPL, it doesn't find anything, because, well, it doesn't have that chip there. And if I go, okay, well, let's see, let's go through analog. And okay, well, ADC, those are A to DC converters. Amplifiers, okay, it's got amplifiers in there. A MUX multiplexer, comparator, digital to analog conversion, and then manual routing. But okay, well, there's not much there. Communications, okay, well, I can see I2C, which is what I'm going to do. But my point being is there is no little block for us to drag and drop this component in. In other words, there is nothing in the program for this sensor. So if we want to use this sensor, we have to create our own API for us. Now, often manufacturers provide an API that's written in either C or C++, but in these applications, what we're going to do is we are actually going to be writing the API for it, so that we can actually see how we would go about doing it. And sometimes when we say write an API, you can almost imagine it as writing a driver. I need to be able to communicate with this chip and have it be interfaced with the embedded controller, and I don't want it to be where I have a bunch of weird commands that I have to run. I want to be able to run things that are simple. For instance, I want to be able to just do a start on this and then maybe say read pressure. Call a function that says read pressure, and it just automatically returns the read pressure. You don't have to sit there and type in every single time all the commands that we're going to have to do in order to read the pressure. Okay, so that's what we're going to be working on. But in order to do that, we have to figure out, well, how does this work? So if you scroll through the data sheet here, you can see it's got a sequence flow chart. It also talks about initial power here. This is important to read, that all circuits are active when powered up, and it enters standby. The user then typically accesses the part and reads the coefficient data. So we always have to read the coefficient data. And then this is the first step that's performed each time a new pressure reading is required, which is initiated by the host sending the convert command. Okay, so there's a convert command we'll have to send. And then it has a conversion time for it to be taken. And then after the conversion has been given sufficient time to complete, the host controller reads the result and calculates the compensated pressure. Barometric/atmospheric pressure value, which is compensated for changes in temperature and pressure sensor linearity. And then this goes into a little bit about that as well. So it starts talking about how to do this. But then what we have here, the next thing it gives us here, this is where we have some good information data here. It gives me the device memory map. So this is not on my embedded controller. This is on the chip that we're going to have. And there are register locations, memory locations for data. And so the address 00 has the most significant byte of my 10-bit pressure data. And then LSB has the least significant byte, so on and so on. And then we have my coefficient data as well that I'll need to have it. And then of course 0 through 1, 0B through 0C through 1, 1 are reserved. And then 0, 1, 2 convert, well, that's start the pressure and temperature conversion. That's the command we do to start the temperature and pressure conversion. And so we now have an idea of how this would work. There's some more information about the actual numbers that we're going to get into, and we'll get into that when we start getting ready to write the code. But then it said, okay, the 10-bit compensated pressure output, Pcomp, is calculated as follows. And then it gives an equation, and here are some of those coefficients. Here's a temperature thing. And then it gives you a formula for to actually calculate the pressure in kilopascals. So you have this compensated pressure, which of course we calculated up here, times 1015 minus 50 over 1023 plus 50. And then it kind of even goes through like an evaluation sequence of how to do these computations, and kind of gives a block diagram here. And then the other thing it tries to talk about is how to do the read and write commands, and it has this hex information for the write, but we don't quite need that. I'll show you why we don't need to do that. But this is again important, the start conversion 0x112 or 0x12. And then again here is like how you would read the thing. You'd set it in the read mode, and then set it to read in the particular data here. And it's also trying to again give you some examples of precisely how that would be done. Now the read coefficient diagram here, this is how to read some of the coefficients. So first note that it does a write command, and this is a write command here, the 0x60. How do I, or 0xc0, how do I know that's a write command? Well, that's what this is, write. And what it does is it writes 0x04. What that does is it actually sets the pointer to the particular location. And I know I'm just kind of talking a lot through the datasheet. I will draw all this out in another video here so that you can see precisely what's going on. And then we proceed to read in the data. So, and it's got a, basically a read result here. And the nice thing about this is it gives you some rough ideas of reasonable numbers. As far as right here, you can look at, we can see if when we are starting it and hook up our temperature and pressure sensors, they should be similar to these four numbers. They're not going to be the same. The reason we have to read those coefficients is these are calibrated at the manufacturer warehouse, and so these coefficients are calibration data that we need to read in order to be able to accurately compute pressures. And then it goes through another computation of calculating what the pressure is. And then the remaining of it is talking about soldering, and there isn't any temperature formula on here. There is one that we can use. As I said, it's not really a great temperature sensor, so we're going to primarily use this just for reading pressure. And so we're starting with this one because it's very simple. All we're going to do is write an API that interfaces with this and reads the pressure. And you can actually have it vary the pressure just by kind of putting your finger on it and stuff like that. But we might also throw the temperature in there even if it's inaccurate, just so that we can have a temperature reading. So that's where we're going to move on from here. So in the next video, what I'm going to do is I'm going to start kind of sketching out exactly the process we're going to need to do in the code to start writing this API. Then we'll write the API. Then after writing the API, we'll actually write a program to show that this works, and then we'll move into another LCD sensor I2C, because the whole point is we'll be able to hook up multiple I2C devices on the same I2C transfer, which the advantage to that is instead of having to use up a bunch of pins for all of the communication to various sensors that you're connecting up, you basically get to just connect everything to the same 2 pins. That's the advantage of I2C, is you can connect multiple devices up in a master-slave configuration. Now, one last thing here, I'm scrolling up here before I end this video, that I forgot to point out here, and it's probably in other areas, but it has the I2C address as being 60. That's what we're going to actually need to know here, the way that our Cypress, the way it works with their I2C APIs. We're going to need to know that the device address is actually 0x60.